Hello everyone, just going to do a quick sound check. This is a impromptu sort of stream day. We're doing like 2 sessions, one now, one a little bit later. This is an impromptu sort of stream. So we'll be starting on the hour when X catches up, and we'll be going to about 4:30. So we're not going to do loads right now. Stuff we'll be doing like a longer session this evening, but just get everything set up and ready. Can we do a new module which is Learn SQL, and it's got about like 130 lessons or something like that. So we'll see how much we get through. Might be able to get through quite a lot very, very quickly, but we will see. 124 lessons. It says 30 hours of content, but I have a feeling we'll get through this a bit quicker than that, but we'll see. Oops, realized I've done these the wrong way around. Right, we should be all up and running now. Yep, Twitter's caught up. I will sort it afterwards. Okay, let's see if we got it back. Yep, okay, right, let's get cracking. No time to waste. Right, let's get stuck into SQL. Get muted a minute. So what is SQL? Structured Query Language, or SQL, pronounced SQL by the in crowd, is the primary programming language used to manage and interact with relational databases. SQL can perform various operations such as creating, updating, reading, and deleting records with a database. So let's watch the video.
One day, I kept my manager staring out the window at a guy shoveling garbage off the street into a truck. He kind of sighed and said, "You know, we're not so different, he and I." And over the years, I've come to understand exactly what my manager meant. As backend developers, we take a bunch of data from one place and shovel it into another place. We're really just kind of moving digital garbage around. That's like the whole job. And the best tool for moving digital garbage is SQL, or SQL, or squeal. So say you're a programmer at Google working on YouTube. Your job is to write code that shovels data from creators' devices, so a video, a title, a thumbnail, up into YouTube's cloud servers and stored in some database. Then, when users are bored at their sister's graduation, they log onto YouTube to find a meaningful distraction. Your job is to write code that shovels all that same video data back out of YouTube servers and down onto the user's devices. SQL, or Structured Query Language, is just the language that we as programmers use to communicate with most relational databases. And it's so popular that databases are broadly categorized into SQL databases and no SQL databases, or no SQL databases, which really just means everything else. So what is a database? Well, really, it's just a program, usually separate from your actual backend application server, that's built to store large amounts of data on disk. And importantly, to store it in a way that makes it fast to access, with advanced filtering and sorting options. You can kind of think of it like a programmatically accessed Microsoft Excel. Now, with Excel, you can move data around fairly manually by typing and clicking, typing and dragging and dropping. A relational database works similarly, and the data is organized into tables of rows and columns. But it's all managed in code, not manually with mouse clicks. Your code automates the creates, reads, updates, and deletes within the database. The code that interacts directly with the database is, you guessed it, SQL. SQL is just a query language that we use to get data in and out of relational databases like MySQL, Postgres, or SQLite. It doesn't matter if your backend programming language is Go, Python, or TypeScript. If your database supports SQL, you can use SQL syntax to get data about a user named Bilbo out of your database. Select first name, last name, age from users where email equals bilbo@boot.dev.
Okie doke. Nice little intro. So, in this module, Cache Pal. So, how many chapters have we got? We've got 11 chapters. Yeah, I think we'll go through this fairly quick. Cache Pal. In this course, we'll be building the database for a pretend PayPal clone called Cache Pal. Storing information related to people's money, transactions, and identity is very important. So we will need to make sure we use proper conventions to build a safe and reliable database architecture that our users can rely on. Assignment. We have provided a simple SQL statement for you that retrieves some records from a table. However, there isn't a people table, and the table in our database is called users. Fix the bug by changing people to users with a selection statement. Oh, let's put our little bonus thing on. Okay. SQL select. So let's write out SQL statement from scratch. A select statement is the most common operation in SQL, often called a query. Select retrieves data from one or more tables. Standard select statements do not alter the state of the database. So select ID from users. Select a single field. So a select statement begins with the keyword select followed by the field you want to retrieve. So just an ID, and then select multiple fields. If you want to select more than one field, you can specify multiple fields separately by commas. Select all fields. If you want to select every field in a record, you can use the shorthand asterisk. After specifying fields, you can indicate which table you want to pull records from using the from statement followed by the name of the table. We'll talk more about tables later, but for now you can think of them like structs or objects. For example, users table might have 3 fields: ID, name, and balance. And finally, all statements end with a semicolon. So assignment. The state of our Cache Pal users table is as follows. It's very common to write queries that only return specific portions of data from a table. Our HR team has requested a report asking for all the names and balances of all our users. Write a query that retrieves all the names and balances from select name balance from users. How do I run it again? Control enter. Okay, control shift enter. Boom, nice. Which databases use SQL? So SQL is just a query language. You typically use it to interact with specific database technology, for example, SQLite, Postgres, MySQL, CockroachDB, and Oracle. Although many different databases use the SQL language, most of them will have their own dialect. It's critical to understand that not all databases create equally. Just because one SQL compatible database does things a certain way doesn't mean every SQL compatible database will follow those exact same patterns. We're using SQLite. In this course, we've used SQLite specifically. SQLite is great for embedded projects, web browsers, and toy projects. It's lightweight but has limited functionality compared to the likes of Postgres or MySQL, two of the more common production SQL technologies. We'll point out to you whenever some functionality we're working with is unique to SQLite. So assignment. One way in which SQLite is a bit different is that it stores Boolean values as integers. The integers are 0 and 1. Select all the ID names and is admin flags from the users table. So select ID name is underscore admin from users. Okay. NoSQL versus SQL. When talking about SQL databases, we also have to mention the elephant in the room, NoSQL. To put it simply, a NoSQL database is a database that does not use SQL, structured query language. Each NoSQL typically has its own way of writing and executing queries. For example, MongoDB uses MQL, MongoDB query language, and Elasticsearch simply has a JSON API. While most relational databases are fairly similar, NoSQL databases tend to be fairly unique and are used for more niche purposes. Some of the main differences in SQL and NoSQL databases are NoSQL databases are used for non-relational. SQL databases are usually relational. We'll talk more about what that means later. SQL databases usually have a defined schema. NoSQL databases usually have dynamic schema. SQL databases are table-based. NoSQL databases have a variety of different storage methods such as document, key value, graph, wide column, and more. So let's have a watch of the video.
SQL isn't web scale. Why don't you use MongoDB? MongoDB is a web scale database. Look, maybe you've heard claims like this before, but let's talk about the real differences between SQL and NoSQL databases, and look at some of the more popular technologies in both categories. So on the SQL side, we've got Postgres, big favorite of mine. You've probably also heard of MySQL and SQLite. There's SQL Server, which is Microsoft's product, and I'll also mention CockroachDB, which is a pretty cool distributed SQL database. Now, there are hundreds of SQL-compatible databases out there, but these are probably just some of the ones you've heard of. Now, MongoDB is probably the most well-known example of a NoSQL database. In fact, some people even use the terms synonymously, which I think is a big mistake. You've probably also heard of Redis, maybe Elasticsearch. Firebase is another really popular one. It's more than just a database. It's kind of a backend as a service. And I'll also mention DynamoDB, which is Amazon's big data store. Now, the first thing you need to understand about the difference between a SQL database and a NoSQL database is that SQL databases tend to be much more similar to each other. They're grouped together in this category because they all have something in common. They all use structured query language to be queried. But NoSQL databases, really the only thing that they have in common is that they don't use SQL. So they're all very different, and frankly, they're not even built necessarily to solve the same types of problems. For example, if I asked a candidate in a back-end interview, hey, would you use Postgres or MySQL to build this CRUD app? And they said, either would work just fine, that would make sense. But if I asked a candidate if we should use Redis or DynamoDB for our caching layer, and they said, it doesn't really matter, then there's no way they're making it to the next round. Now, SQL databases tend to be more general purpose. Now, that's not always true, but at the end of the day, a SQL database is just a database that supports SQL. So you can have a more specialized SQL database, but most of the popular SQL databases are good for general purpose starting points for web applications. One exception might be SQLite, which is built for small use cases where you want to embed the database directly inside your application. And NoSQL databases, on the other hand, they tend to be very specialized. NoSQL databases are usually built for a specific purpose that a general purpose SQL database doesn't handle as well. Again, one exception is probably MongoDB, which is a fairly general purpose database. It just happens to not use SQL. For example, Redis is mainly used for caching in-memory data for super low latency access. It's common for web apps to use Redis together with a SQL database, and they use Redis as sort of this caching layer. Elasticsearch is another example of a very specifically designed NoSQL database. It's designed for dynamic search and aggregations. It powers things like the eBay search bar. It handles fuzzy text matching and ranking of results. Another one is Firebase, a Google-hosted product. It's really built for real-time mobile apps. And the last one I'll mention again is DynamoDB. It's built to store very large amounts of data at scale. The trade-off is that you kind of have to denormalize your data, and you can't write the same flexible queries that you would inside a normal SQL database when you use it. The main point here is that an SQL database is any database that you can interact with using SQL syntax, and a NoSQL database is just any database that doesn't have that. When you're deciding which database to use for your application, you really need to weigh the pros and cons for your very specific use case. For most simple CRUD-based web applications, something like Postgres is gonna work just fine. It's a general purpose database that can handle a good amount of scale. But as your application's data grows, or if you have a very niche specific use case, you can introduce other database technologies to your stack at that point.
Good breakdown. So these is just an iteration of what you said before. So each NoSQL database tends to use different query languages. Blank compatible databases tend to be more similar in their functionality than, so SQL compatible databases tend to be more similar in functionality than NoSQL databases. Which type of database always uses table structures? SQL. Comparing SQL databases. So let's dive deeper and talk about some of the popular SQL databases and what makes them different from one another. Some of the most popular SQL databases right now are Postgres, SQL, MySQL, Microsoft SQL Server, SQLite, and many others. While all these databases use SQL, each database defines specific rules, practices, and strategies that separate them from competitors. So SQLite versus Postgres SQL. Personally, SQLite and Postgres SQL are my favorites from the list above. Postgres is a very powerful open source, production-ready SQL database. SQLite is a lightweight, embeddable, open source database. I usually choose from one of these technologies when I'm doing SQL work. SQLite is a serverless database management system that has the ability to run within applications. This database management, okay. Whereas Postgres SQL creates a client-server model and requires the server to be installed and listening to a network similar to HTTP server. See the full comparison here. We use SQLite in this course. In this course, we'll be working with SQLite, a lightweight and simple database for most backend web servers. Postgres is a more production-ready option, but SQLite is great for learning and small systems. Assignment. Let's take a look at how SQLite does not enforce type checking. Notice that within the create table statement, name is defined as a text field. Run the code and take a look at the results. Don't submit yet. On line 3, change the string Montgomery Burns to 1 and run the code. Notice even though we defined the name as a text field, SQLite allowed us to use an integer. Like Python and JavaScript, SQLite has a loose type system. You can store any type of data in any field regardless of how you defined it. Remember, just because you can do something doesn't mean you should. To pass the assignment, submit the code in the altered state where a record with the ID 2 has a name of 1. So, tables. So to create a new table in a database, you use the create table statement followed by the name of the table and the field you want in it. Each field name is followed by its data type. We'll get to the data types in a minute. It's also acceptable and common to break up the create table statement with some white space like this. Assignment. Let's begin by building a table for CashPal database. Create the people table using the following fields. So create table, and was it people? It's going to be ID integer, tag, text, name, text, age, integer, balance integer is underscore admin boolean. Oh, peasy. Create table practice. So in most relational databases, a single table isn't enough to hold all the data we need. We usually create a table per entity. For example, social media application might have the following tables. We need to create users, posts, comments, likes. We need to create a table that tracks the transactions between CashPal users. Create a transactions table with the following fields. So create table transactions. It's going to be ID integer, recipients ID integer, sender ID integer, note text amount integer. Just go for it straight away. Bosh go. So altering tables. We often need to alter our database schema without deleting it and recreating it. Imagine if Twitter deleted its database each time it needed to add a feature. That would be a disaster. Your account and all your tweets would be wiped out on a daily basis. Instead, we can use the alter table statement to make changes in place without deleting any data. So alter table. So with SQLite, an alter table statement allows you to alter the table. We should rename to that. Okay. Alter table contractors, rename column. Okay. Rename a table or column, add or drop a column. Unlike some SQL databases, SQLite does not support adding multiple columns in a single alter statement. Each column must be added in a separate alter table command. So assignment, we need to make some changes to the people table. Okay. At the minute, we have these 6 columns shown as rows, so we can display data types. Rename the table to users. So we're going to start with alter table. Alter table users. Rename tag column to username. So it's rename column tag to username, and add password text column. Alter table users. What was it? Add column. Add column. Password text. Oh, people. Whoops. So alter table people, rename to what was it, users? Intro to migration. So a database migration is a change to the structure of a relational database. You can think of it like a git commit and git. But for your database schema, every migration records how the structure of the data evolves over time. So for example, we can previously used alter table statement to add a new column. We were performing a migration. Migrations are essentially for adapting a database to changing requirements, fixing mistakes, and rolling out a new feature. In a team setting, migrations ensure everyone applies the same changes in the same order. Good migrations are small, incremental, and ideally reversible changes to a database. As you can imagine, when working with large databases, making changes can be scary. We have to be careful when writing database migrations so that we don't break any systems that depend on the old database schema.
Database migrations are kind of like unit tests. Most people suck at writing them, but they do like to talk about how important they are. Now, you're probably doing migrations wrong, or more likely you're not even doing them. So let's talk about the right way to do them. Say that we have a users table with ID, username, and password columns. The database is currently being used in production, and now it's time to add a new feature, and that feature requires a birthday column for each user. The right way to do this isn't to just connect to the production DB with PSQL and run a quick add column. The right way is to create a migration file. That add column query goes inside it, and our system should be configured to run our migrations whenever we deploy new code changes. Now, when we want to create a copy of the database, or we need to spin up a new local development environment, we just run all of our migrations one after the other, and the schema, tables, columns, indexes, that kind of stuff, will always match. Now, this type of migration, where we're just adding a new column or a new table, tends to be really safe. None of the currently running queries in production are going to care about this birthday column, so when we add it, those queries will still work. They'll just ignore the new column. See, a good migration needs to think about two things. One, the old, currently running version of the code, and two, the new version of the code that will run after the migration is complete. A lot of developers forget about the old version. They write a migration, they test their new code on the new schema, and then they just deploy it. But as the migration deploys, the app breaks for the couple of minutes when the old version is still running, but with the new schema. So, for example, say we create a migration that removes a password column and adds a Google ID column. Maybe we're no longer storing user passwords because we only support sign-in with Google. Now, if we run this migration, but the currently running version of the app runs a select password from users query, then user logins are going to be broken until the new version of the code that doesn't use that field is deployed. So you might think, well, great, let's just deploy the code first. But that doesn't work either because the new code depends on the new Google ID column that's in the migration. So the answer here is to do a multi-phased rollout. Step 1, we run a migration that adds the new Google ID column, and this is safe. Step 2, we deploy the new code that uses the Google ID column, but not the password column. Step 3, we run a cleanup migration that just removes that unused password column. Okay, so creating and removing columns and tables is pretty straightforward, but what if we want to update an existing column? Well, generally speaking, the safest thing is to just not do that. At least not directly. It's okay to add an index to an existing column for performance reasons, because that would break any of the currently running queries. But what you don't want to do is rename an existing column that's being actively used in production. Instead, we should do another more complicated multi-phase rollout. Step 1, run a migration to create the new column. Step 2, copy the data over from the old column into the new column. Step 3, deploy the code that uses the new column, but not the old one. And step 4, this is very important, recopy the data from the old column to the new column to catch anything that was missed between the initial copy and the code deployment. And then step 5, just run a migration to remove the old column. Now, to be fair, this is kind of a lot of work. If your team just doesn't have the resources to do that, a cheat some companies will use when the migration gets really hairy is just to schedule some downtime. You can literally just turn off your application and tell your customers, hey, the whole site's going to be down for the next 30 minutes while we do a big update to our database. I want to be clear, this should only be a last resort, and you should only do it if the migration is super hairy and you feel like the time trade-off isn't worth it. Most good engineering organizations tend to avoid downtime at all costs.
Yeah, well put. So example of a bad migration. So let's say the cache pile backend runs this SQL regularly. Select all from people. If we rename the table from people to users in a migration but forget to update the code, this query will break because the people table no longer exists. The right approach. So deploy the migration to rename the table. Immediately deploy new code that uses a new query. Migrations must be carefully coordinated with applications to changes to avoid outages. So which of the following statements about migrations are false? You can be fast and loose when migrations. A bad migration is easy to fix. If only it were. Well-written migrations are reversible. Which one? False. Reversible migrations are incremental changes made to a database. A good migration takes into account any systems that rely. I think it's the first one because it's false. Okay, up migration. So to manage migrations, we use a simple system based on up and down directions. The up migration applies changes to move your schema forward. The down migration rolls those changes back to the previous state. This allows developers to safely move between versions of the schema during development and production rollouts. Let's write an up migration to add new features to our database. So, add additional columns to the transactions table. We want to know whether or not the transaction was successfully completed between two users. We also want our database to track the type of transaction. Our transactions table looks like this at the moment. Create the following up migrations. So, add the Boolean was successful column to transactions table. So, alter table. Transactions is it add column was underscore successful Boolean. So alter table again. Transactions, add column, transaction, section underscore type, text. Okay, that's the up part. Down migration. The migration we applied ended up causing trouble in production. It's possible the app wasn't ready for the new columns. In situations like this, how many we got left? It's ready for the new columns. In situations like this, we need to roll back changes safely using a down migration. So why down migrations matter? Down migrations allow us to undo changes introduced by an up migration. Quickly recover from bugs or compatibility issues in production. Keep our schema consistent across environments, local staging, and production. A well-written down migration should completely reverse the changes made in the up migration. In our case, that means removing the two columns we added. So complete the following migration. Drop the
Okay, so you think you're a responsible developer because you write well-documented migrations for your database schema. But what happens when one of your migrations is bad? Normal database migrations, the ones that you run to get your database into the correct state for your application, those are called up migrations. They take your database from the old, out-of-date state into the new, proper working state. Now, to be fair, a lot of engineering organizations get away just fine without writing down migrations at all. They just move forward, and in the event of something going wrong with an up migration, they just roll out another up migration that fixes it. And this really can work, especially if you're on a small team. But as team size and application complexity grows, you usually want more safeguards in place. In particular, you probably want the ability to roll back a change when something goes wrong. Now, it's always easy to roll back code changes. Just go back to the last git commit and deploy that version. But databases are a little trickier. Say you deploy code that doesn't need a bio column anymore. So you run an up migration that drops that column. Then, 10 minutes later, you realize there's a bug in the code. So you need to go back to the old version of the application that requires that bio column. You can't just revert the code anymore, because now it's going to break because the bio column is gone. So that's where down migrations come. The idea is that each time you write an up migration, you also write a down migration that can be used to undo. So if the up migration removes bio column, the associated down migration re-adds it. If an up migration creates a notifications table, then its down migration removes it. The down migration should always be the inverse of the up migration. And it's really only used in the case of failure or a rollback. Now, it's very important to remember that while down migrations can fix the schema of a database so that the code will work, they usually aren't written in a way that will actually recover the lost data. In other words, we can add that bio column back, but all those user bios aren't going to be there anymore. They're just going to be blank. So the code will still work in the sense that the queries aren't going to throw errors, but the data won't be there. So to solve those problems, you need a backup strategy that you can go pull that old data from, but that's another topic.
Yep, so let's have a little run of this. Oh, don't need that part. Happy days. So migration review, let's look at a more realistic migration that reflects a common evolution. So example, the project's table is being renamed to initiatives to better reflect how teams plan and track long-term work. We also want to record when each initiative officially launched. So up migration, so alter table projects, rename it to initiatives, and then add the launched at column as a timestamp. So down migration, alter table initiatives, drop column launched at, alter table initiatives, rename to projects. So this pair of migrations is reversible and safe. If something breaks, we can undo it. Real world migration tools. So in real world projects, we don't run raw SQL migrations. We use tools that help track which migrations have been applied, organize migrations in files, apply and roll back safely. So popular tools. So Goose in Go native Go tool, Flyway for Java, simple file based, Liquid base for Java, more config heavy, Alembic for Python for SQL Alchemy, Prisma Migrate Node.js works with Prisma ORM, example workflow with a tool. This will vary according to the tool you use, obviously. Write migration files, apply them using a CLI. Your tool logs which migrations ran, prevents duplicate migrations. So version control for your schema. Migration files are committed like code. They travel with your project, so teammates and CI systems always apply the same schema changes in the right order. Why are good migrations written in a reversible way? They're not. So that if something goes wrong, the change can be rolled back, because you should always roll back changes before applying new ones. So you can roll back. Will database migrations often be coupled with application update codes? I guess so. So, SQL data types. SQL as a language can support many different data types. However, the data types that your database management system supports will vary depending on the specific database you're using. SQLite only supports the most basic types, and we're using SQLite in this course. So SQLite data types. Let's go over the data types supported by SQLite and how they are stored. So null, integer, so null is a null value, integer, assigned integer stored in 0, 1, 2, 3, 4, 5, 6 or 8 bytes, real, floating point value stored as a 64-bit IEEE floating point number, text string stored using database encoded such as UTF-8, blob, short for binary large object, and typically used for images, audio, or other multimedia. Boolean. Boolean values are written in SQL-like queries as true or false, but they're recorded as 1 or 0. Boolean values. It's important to note that SQLite does not have a separate Boolean storage class. Instead, Boolean values are stored as integers. 0 is false, 1 is true. It's not actually that weird. Boolean values are just binary bits after all. SQLite will let you write your queries using Boolean expressions and true or false keywords, but it will convert the Booleans to integers under the hood. So how is a true Boolean value stored and represented in SQLite? The string true, the string false, 1 and 0. 1 is true. All SQL databases support the same data types. Nada. What type would you use to store a user's email? Text. So, posts table. You're working on CashPal's latest social media feature named CashPal Chatter, which aims to revolutionize financial discussions online. Users can make a typical social media post that contains a picture of their latest purchase along with text and some other information. You've been assigned to create the new posts table. Assignment: write an SQL statement to create a new table named posts, which should contain the following columns. So create, uppercase, create table, posts. Use the data types that make the most sense for the given name. So ID is going to be integer. Image underscore URL equals text description is text. Author ID is integer, and is sponsored sponsored Boolean. Use it for ID columns. We assume we can use integer, so try that. Happy days. Pushka. Post table migration. So CashPal Chatter is a huge hit. After several weeks of use, the engineers at CashPal. Oh, one moment. That doesn't happen often, but never mind. CashPal Chatter is a huge hit. After several weeks of use, the engineers at CashPal have decided that some changes need to be made to our post table. You have been asked to write an up migration to alter the table. So write an up migration for post table that achieves the following. The author ID column should be renamed to poster ID. So alter table posts, rename column author underscore ID to poster underscore ID. Add a new column named post, add a new column, is edited with a Boolean type, is underscore edited. And then drop the is sponsored column, is sponsored column. Whoops. Oh no, I went the wrong way. Okay. Ta-da! So we did that, and now we're on to the next part. Constraints. In SQL, a cell with a null value indicates that the value is missing. A null value is very different from a zero value. Constraints. When creating a table, we can define whether or not a field can or cannot be null, and that's a kind of constraint. We will cover constraints in more detail soon. For now, let's focus on null values. So assignment, we didn't force any constraints on our tables when we created them, and it was allowed for null entries. In creating a table, you can define whether or not a field can or cannot be null. Let's create a constraint. That's kind of constraint. We'll soon. Okay. We didn't force any constraints on our table when we created them, and it has allowed for null entries to make their way into our table. Let's take a look at the transactions table to see what those null values look like. Write a query to select all the fields on the records of the transactions table. So select all from transactions. Notice that both transaction type and was successful fields have null values in all three records. Nulls are represented as blank cells in our system. That's because we ran our migration in the previous exercise after creating three records. Okay. Constraints. A constraint is a rule we create on a database that enforces some specific behavior. So, for example, setting a not null constraint on a column ensures that the column will not accept null values. If we try to insert a null value into a column with the not null constraint, the insert will fail with an error message. Constraints are extremely useful when we need to ensure that certain kinds of data exist within our database. So defining a not null constraint. So the not null constraint can be added directly to the create table statement. So primary key, the primary key constraint uniquely identifies each row in the table. Text unique. The unique constraint ensures that no two rows have the same value name. And not null. The not null constraint ensures that the title column cannot have null values. So SQLite limitation. In other dialects of SQL, you can add constraint within the alter table statement. SQL does not support this feature. So when we create our tables, we need to make sure we specify all the constraints we want. Here's a list of SQL features SQLite does not implement in case you're curious. So the assignment. Thankfully, all the tables we have created for Cashbell up to this point have been for testing purposes. Now that we have a better understanding of constraints, let's rebuild our database with the proper constraints and tables. So create users table with the following fields and constraints. So create table users ID integer primary key name text not null. Age, integer, integer, not null. Country code, country code text, not null. Username, text, not null. Oh, and unique. Password, text, not null. Is, let's call admin, boolean. I'm pretty confident on this one, so let's just hit it. Boom. Primary keys. So a key defines and protects relationships between tables. A primary key is a special column that uniquely identifies records within a table. Each table can have one and only one primary key. Your primary key will almost always be the ID column. It's very common to have a column named ID on each table in a database, and that ID is the primary key for that table. Not two rows. No two rows in that table can share an ID. A primary key constraint can be explicitly specified on a column to ensure uniqueness, rejecting any inserts where you attempted to create a duplicate ID. So assignment. Run the code. Notice there's a bug. There's a violation of a primary key constraint on the ID column. Fix the data that's been inserted. When working with integer IDs, it's best to practice to increment ID by 1 for each successive insert. Follow this convention when fixing the bug. Oops, keep going. Ta-da! Easy peasy. How long got left on the thing? Foreign keys. So foreign keys are what make relational databases relational. Foreign keys define the relationships between tables. Simply put, a foreign key is a field in one table that references another table's primary key. So creating a foreign key in SQLite. So create a foreign key in SQLite at table creation. After we define the table fields and constraints, we add a named constraint where we define the foreign key column and its references. Here's an example. So create table departments, ID integer primary key, department name text not null. Create employees, ID integer primary key, name text not null, department ID integer, constraint. Okay, constraint, foreign key departments. Foreign key is department ID, so that's the name for us, and references department's ID. Okay, in this example, an employee has a department ID. The department ID must be the same as the ID field of a record from the departments table. FK departments is the specified name of the constraint. Constraint FK departments create a constraint called FK departments. Foreign key department ID, make this constraint a foreign key assigned to the department ID field. References, department's ID. Link the foreign field ID from the department's table. So assignment. Our users table stores the country our users are from in a country code field. We need some additional data about countries like their name, but we don't want to bloat our users table with all that country data. The locations team at CashPal has created a countries table, and we can link a user to their country by setting a foreign key in the users table. Creating a foreign key without the constraint keyword means the name of the constraint is auto-assigned. Creating a foreign key without the constraint keyword means that the name of the constraint is auto-assigned. Take a look at the code. There's an issue with the insert statement again. Fix up the data so no foreign key constraints are violated. You'll need to reference the setup in the up SQL tab. To fix. So schema. We've used the word schema a few times now. Let's talk about what that word means. A database's schema describes how data is organized within it. Data types, table names, field names, constraints, and the relationships between all those entities are part of a database's schema. There is no perfect way to architect a database schema. When designing a database schema, there typically isn't a correct solution. We do our best to choose a sane set of tables, fields, constraints that will accomplish our project's goals. Like many things in programming, different schema designs come with different trade-offs. How do we decide a sane schema architecture? So let's use CachePal as an example. One very important decision that needs to be made is to decide which table will store a user's balance. As you can imagine, ensuring our data is accurate when dealing with money is super important. We want to be able to keep track of a user's current balance, see the historical balance at any point in the past, see a log of which transactions changed the balance over time. There are many ways to approach this problem. For our first attempt, let's try the simplest schema that fulfills our project's needs. So assignment. The architecture team at CachePal has decided on a single transactions table. The transactions table stores individual transactions, and we can keep the track of the current balance on each transaction record. If we want the current balance, we can just look at the most recent transaction. Create the transactions table with the following fields and constraints. Okay, so create table transactions integer primary key sender underscore ID integer recipient underscore ID integer memo text not null amount integer not null. integer, not null. Didn't ask us to put a thing on it. So relational databases. We have been using the term relational quite a bit. It's time we actually go over to what that means. A relational database is a type of database that stores data so that it can be easily related to other data. For example, a user can have many tweets. There is a relationship between user and their tweet. In a relational database, data is typically represented in tables. So each table has columns or fields that hold attributes related to the record. Each row or entry in the very good to see. Each row or entry in the table is called a record. Typically, each record has a unique ID called the primary key. So example, relational database. So students, student courses, and then courses. So here's an example of a small relational database. This database has 3 tables: students, courses, and student courses. The student courses table manages the relationship between students and the courses table. Example 1, Sam. So Sam has the ID of 1. We can find Sam's courses by looking in the student courses for the records that match his student ID. Example 2, ASP.NET MVC. So ASP.NET MVC has an ID of 2. We can find all the students enrolled in ASP.NET MVC course by checking the students course table. So how many courses is Sam enrolled in? So Sam is in 1, 1, 2, 3, 3. Relational, same question. How many students are in the ASP.NET MVC course? So 2, just 1. Relational versus non-relational databases. Relational versus non-relational databases. So the big difference between relational and non-relational databases is that non-relational databases nest their data. Instead of keeping records on separate tables, they store records within other records. To oversimplify it, you can think of non-relational databases as giant JSON blobs. Giant JSON blobs. If a user can have multiple courses, you might just add all courses to the user record. This often results in duplicate data within the database. That's obviously less than ideal, but it does have some benefits that we'll talk about later in the course. Relational database. Yep. So then non-relational database. Blank databases often duplicate data, while blank databases typically don't. So non-relational versus relational. Non-relational databases connect similar entities by using nested data. Lubber. CRUD. Okay. CRUD is an acronym that stands for Create, Read, Update, and Delete. These 4 operations are the bread and butter of nearly every database you'll create. HTTP and CRUD. So the CRUD operations correlate nicely with the HTTP methods we learned in Learn HTTP Clients course. Already done that one. HTTP post is create, HTTP get is read, HTTP put is update, HTTP delete is delete. Assignment. We've created a table for you called CRUD. It's a toy table we're using for interview practice at CashPal. So determine which SQL command can be used for a read operation. Hold on. We created a table for you called CRUD. It's a toy table we're using for interview practice at CashPal. Determine which SQL command can be used for a read operation and use it to read all the fields in all the records in the CRUD table. So I guess just select all from CRUD. Is that it? Just a rote memory with this one. So insert statement. Tables are pretty useless without data in them. So in SQL we can add records into a table using insert into statement. When using the insert statement, we must first specify the table. Table we're inserting the record into, followed by the fields within that table that we want to add values to. Example, insert into statement. So let's start manually adding some of the records to our users table. So take a look at the create table statement in the setup code in the up SQL. So it has to have ID, name, country code, username. Take a look at the blah blah blah. And use the information to insert the following records into the table. So insert into users. And it's going to be values. The first value is going to be 1. Second value is going to be David. Second value is going to be 34. It's going to be US. It's going to be David Dev. It's going to be insert practice, and then 0. So password, country code. That's adding all of it, yep. And then the next one's going to be 2. Samantha 29. BR. Sammy 93, was it? So it's going to be adding records. HTTP CRUD database lifecycle. So it's important to understand how data flows through a typical web application. The front end processes some data from the user input. Maybe a form is submitted. The front end sends the data to the server through a HTTP request, maybe a post. The server makes a SQL query to its database to create an associated record, probably using an insert statement. Once the server has processed that the database query is successful, it responds to the front end with a status code, hopefully a 200 level code success. A front end typically communicates with the database directly to add new records. Wrong. The create in CRUD maps to which SQL statement the HTTP method. Create, it's insert or post. So auto increment. Yeah, let's try and get this this section done. So auto increment. Many dialects of SQL support an auto increment feature. When inserting records into a table with auto increment enabled, the database will assign the next value automatically. In SQLite, an integer ID field that has the primary key constraint will auto increment by default. So IDs. Depending on how your database is set up, you may be using traditional IDs or you may be using UUIDs. SQL doesn't support auto-incrementing a UUID, so if your database is using them, your server will have to handle the changing UUIDs for each record. Using auto increment in SQLite. So we are using traditional IDs in our database, so we can take advantage of the auto increment feature. Different dialects of SQL will implement this feature differently, but in SQLite, any column that has the integer primary key constraint will auto increment. So we can omit the ID field when using the insert statement and allow the database to automatically add that field for us. So assignment. Let's add some more records to our users table, but allow the database to automatically increment the ID field and add the following records to the database. I'm just going to copy this because I want to type it all out. And we delete this. So it's going to be, Lance needs 20. It's from the US and is Lance Chur. It's going to be Boot.dev is best. And the next one's going to be Tiffany, and she's 28. US, Tiffaroon, and auto increment. Auto increment. Whoops. Oh, that's why. Ta-da! Manual entry. So, manually inserting every single record into a database would be extremely time-consuming task. Working with raw SQL, as we are now, is not super common when designing back-end systems. When working with SQL within a software system, like a back-end web application, you'll typically have access to a programming language such as Go or Python. For example, a back-end server written in Go can use string concatenation to dynamically create SQL statements, and that's usually how it's done. So SQL injection. The example above is an oversimplification of what really happens when you access a database using Go code. In essence, it's correct. String interpolation is how production systems access databases. That said, it must be done carefully to not be a security vulnerability. We'll talk more about that later. So every time someone creates an account on Boot.dev, Alan or Lane has to manually add them to the database by hand writing SQL query. I think we might be past that. Within backend systems, SQL queries are typically written by hand, generated by code. So count. I think what we do is we get to the end of this, we'll wrap it up for this session and come back later and do a second stint. Okay. Have I got any tissues on me? I do. Don't know why I've gone technically awesome. Count. So we can use a select statement to get a count of the records within a table. This can be very useful when we need to know how many records there are, but we don't particularly care what's in them. So here's an example in SQL. So select count all from employees. The asterisk in this case refers to column name. We don't care about the count of a specific column. We want to know the number of total records, so we can use the wildcard. Assignment. So here is the current state of our users table. Business strategy team at CashPal wants to know how many users of the app we have. We can't use the ID number to calculate the count because the user accounts can be deleted. Use the count statement to retrieve the number of records in the users table. So select count all from users. Eight. Wow, groundbreaking app. HTTP could database lifecycle. So we talked about how a create operation flows through our app application. Let's talk about a read. So get users backend server, select table rows, JSON object goes back. Let's talk through an example using the CashPal app. Our product manager wants to show profile data on a user's settings page. Here's how we could engineer that feature request. First, the front end web page loads. The front end sends a HTTP GET request to a user's endpoint on the backend server. The server receives the request. The server uses a select statement to retrieve the user's record from the users table in the database. The server converts the row of SQL data into a JSON object, sends back to the front end. So the HTTP method that generally corresponds with a SQL select statement in HTTP is get. What happens first? A select statement is executed, a JSON response is sent, a get request is made. Get request is made. The where clause. We've only got 3 potions left, so we'll save it for the session later. Let's try and get to the end of this. In order to keep learning about CRUD operations in SQL, we need to learn how to make the instructions we send to the database more specific. SQL accepts a where statement within a query that allows us to be very specific with our instructions. If we were unable to specify the record we wanted to read, update or delete, making queries to a database would be very frustrating and very inefficient. Using a where clause. Say we had over 9,000 records in our users table. We often want to look at specific user data within that table without retrieving all the other records in the table. We can use a select statement followed by a where clause to specify which records to retrieve. The select statement stays the same. We just add the where clause to the end of the select. Here's an example. This will select only field name of any user within users table where the power level field is greater or equal to 9,000. So it's over 9,000. We need to know the username of all the users in our users table that have admin privileges. Retrieve them. Okay, select username from users where where is admin is equal to true. Easy sneezy. Finding null values. So you can you can use a where clause to filter values by whether or not they're null. So is null, select name from users where first name is null, is not null, okay? Assignment. The way we store transactions in CashPal is interesting. We store a user ID field on the transactions table. That user is the owner of the transaction, and a user ID is never null. Whenever the owner of the transaction receives money, the sender ID will not be null. It will be the user ID of the sender. The recipient ID will be null. Whenever the owner of the transaction sends money, the recipient ID will not be null. It will be the user of the recipient. The sender ID will be null. Select all rows and their columns from the transactions table where the owner of the transactions receives the money. So select all from transactions where the owner of the transactions is receiving money. Where sender sky ID is not null. So don't suppose it matters which way around you do it. You do it multiple ways. Delete. When a user deletes their account on Twitter or deletes a comment on a YouTube video, that data needs to be removed from its respective database. Delete statement. So a delete statement removes all records from a table that match the where clause. As an example, delete from employees where ID is equal to 251. This delete statement removes all records from the employees table that have an ID of 251. Assignment. Samantha, one of our CashPal users, has opted to delete her account and stop using our app, which makes us sad. Anyways, we need to remove her record from the database. Delete Samantha's records from the user table. So delete from users where ID equals, and who is it? Samantha. Bingo. The danger of deleting data. So deleting data could be a dangerous operation. Once removed, data can be really hard, if not impossible, to restore. Let's talk about a couple of common ways back-end engineers protect against losing valuable customer data.
Why is this? Developers are usually the ones that are first to admit their code base is a flaming pile of garbage. Frankly, they're surprised that anyone pays to use the app that they've built. It's props. Your team is only one backup away from potentially wiping out all of your customers' data. A backup strategy is usually a good idea. So let's talk about a few different database backup strategies. The most common strategy is snapshots. They're taken regularly on some interval and stored on a separate server. A lot of companies I've worked for in the past just do daily snapshots. For example, every night at midnight, an automated task runs that copies all of the tables from the database into cold storage somewhere. Snapshot data doesn't necessarily need to be easy to access, like you don't need to be able to query it live, but it should of course be retrievable. In the event of a disaster, we need a way to take the data from the snapshot and restore it back into production. Now, there is a big problem here. If we're just taking a snapshot once daily and something bad happens, we're going to irreversibly lose all the data that happened between the last snapshot and when disaster actually struck. A simple way to mitigate this would be to do hourly snapshots instead of daily ones. But you still have the problem, just on a scale of minutes instead of hours. Now, to be fair, for many small companies, snapshots at an hourly or daily rate are just fine. Hopefully you never lose your production database, but if you do, you're only going to lose a couple of hours of data, and there's a good chance that only a small number of users will be impacted. But it does depend entirely on the type of data you're storing and what your risk tolerance as a company is. So let's talk about a much more robust option. Say you can't afford to lose any data. What you need is a system that logs all changes in real time to some sort of backup log. For example, when you insert a new record and you run that query, you also log that data to a secondary location in real time. And the difference is that it needs to be an append-only log. That way, delete and update operations don't actually remove any data from it. It should log the new state of the record, like the new value or the fact the record was deleted, but it shouldn't delete the old state entirely. The good news is that if you're using an industry standard managed database, most of them actually have point-in-time recovery systems like this already built in, so you don't need to build it from scratch. You just need to make sure that it's enabled and you're paying for it. And finally, the most important thing is that if you never test your backups, they might as well not exist. It's super common for an engineering team to think they have a good backup system, but then disaster strikes and they go to the backups only to find that half of the tables have never been backed up, or the backups have silently been failing for the last 3 months. So regularly test your backups and make sure that your recovery strategy actually works before you need it to.
Yeah, wise words. And automate that process of testing if possible, really. So strategy 1, backups. So if you're using a cloud service like GCP's Cloud SQL or AWS's RDS, you should always turn on automated backups. They take an automatic snapshot of your entire database on some interval and keep it around for some length of time. For example, the Boot.dev database has a backup snapshot taken daily, and we retain those backups for 30 days. If I ever accidentally run a query that deletes valuable data, I can restore it from the backup. You should have a backup strategy for your production databases. And then soft deletes. A soft delete is when you don't actually delete data from your database, but instead just mark the data as deleted. For example, you might set a deleted at date on the row that you want to delete. Then in your queries, you just ignore anything that has a deleted at date set. The idea is that this allows your application to behave as if it's deleting data, but you can always go back and restore any data that's been removed. You should probably only soft delete if you have specific reason to do so. Automated backups should be good enough for most applications that are interested in protecting against developer mistakes. So you should have automated backups being taken of a production database. You should almost always. A soft delete is where you make a row as delete instead of actually removing the data. Delete some data, but it's not actually removed from the database for 30 days. Delete some data by asking your database in a nice shooting voice, usually with a please delete data from a snapshot. So it's just doing that. Oh, sharp shirt chest. Next time. So whenever you update your profile picture or change your password online, you are changing the data in a field on a table in a database. Imagine if every time you accidentally messed up a tweet on Twitter, you had to delete the entire tweet and post a new one instead of editing it. Well, that's a bad example. They do have editing tweets now, though. Update. Update statement. So the update statement in SQL allows us to update the fields of a record. You can even update many records depending on how we write the statement. So an update statement specifies the table that needs to be updated, followed by the fields and their new values by using the set keyword. Lastly, a where clause indicates the record or records to update. So update employees set job title equals blah 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 salary to that, where ID is that. So assignment, we need to update Lane's record in our users table. He founded cash pal, but he's not even the recognized as an admin. Update Lane's record within the users table. So update users table set is admin equals Can you say true, or it has to be one? True. Where ID, where is Lane? He's at the bottom. Where ID equals 9. Object relational mapping. Okay, so there's a few on this. Okie doke. An object relational mapping, or ORM for short, is a tool that allows you to perform CRUD operations on a database using a traditional programming language. These typically come in the form of a library or framework that you can use in your backend code. The primary benefit of ORM provides that is that it maps your database records to in-memory objects. For example, in Go, we might have a struct that we use in our code. So use a struct. This struct definition conveniently represents a database table called users, and an instance of the struct represents a row in the table. So example, using an ORM. So using an ORM, we might be able to write simple code like this. So user generates an SQL statement and runs it, creating a new record in the users table. Example, using straight SQL. So using straight SQL, we might have to do something a bit more manual. So insert into users, ID, blah, 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 values like this. Should you use an ORM? That depends. An ORM typically trades simplicity for control. Using straight SQL, you can take full advantage of the power of the SQL language. Using an ORM, you're limited by whatever functionality the ORM has. If you run into issues with a specific query, it can be harder to debug with an ORM because you have to dig through the framework's code and documentation to figure out how the underlying queries are being generated. I recommend you doing projects both ways so you can learn about the trade-offs. At the end of the day, when you're working on a team of developers, it will be a team decision. When using ORM, you write a lot of raw SQL, call methods and functions made available through via the ORM's API. One advantage of ORM is that it makes your code less verbose, is easier to debug at low level, gives you more control of your database, and shows faster queries. It's just less verbose. Should you use ORM? It depends on the project and team. And the last two, user count. So CashPal has a dashboard on its website that shows statistics on where users are located. One of your QA team members is concerned because the number of users located in the US looks pretty small. So the assignment, write a SQL query that returns the count of every record from the users table that has their country code as US. So select all from, I guess it's like count all from users where country code is equal to US. Remember that we blah 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 blah. Well, I already know that. Is that right? Bingo. Last one in this section. Update country codes. So using our previous query, we've noticed that some of the records were incorrectly saved with a country code value of USA instead of US. Assignment, write an SQL statement to update the country code value from USA to US for all user records, ensuring that only those records initially mapped to USA had changed. So I guess I've forgotten the update update users set country underscore code equals, and it was US where country code is equal to USA. Boom. Okay. So basic queries. Then we're going structuring. Let's have a look. Structuring. Oh, aggregations. Subqueries. Normalization. Whoa. Joins. And then performance. So we might not get through all this tonight, but we're gonna drop this for now. We're gonna finish the stream. We're gonna come back a little bit later and do the next set. So, like I said, that's it for now. So, I'll see you in a bit.